Simulation in research is not just about the finite element analysis. It's not just about the colorful stress plots inside a software. Simulation at its core is the act of taking a phenomena, whether it comes from biology, chemistry, physics, or engineering, and translating it into mathematics. It's about observing something real, like water flowing in a pipe, or stress inside of a structure, or blood moving through the artery, or heat diffusing through a material. Then we describe it in mathematical form. Why do we do that? Because when something is written in mathematics, we gain control over it. We can experiment without physically building anything. For example, we can test whether a heart stent will fail under physiological loads before it's ever implanted in the human body. This is a critical situation where understanding the system before finally implementing it is crucial. Mathematics gives us a safe laboratory. Simulation allows us to explore, test, predict, and optimize long before reality forces us to pay the cost of failure. In this video, we're gonna explore some of the algorithms used to implement the simulation softwares. Before we even talk about the finite element and other advanced methods, we need to clarify something very important. The first and most powerful form of simulation is analytical modeling. When we say analytical, we mean solving the governing equation or the complex differential equation, like the one we mentioned earlier in the videos, directly, without simplifying or assuming, unlike the numerical methods, that contains a lot of simplification and error. Sometimes a simple analytical equation derived carefully from the physics can give you more insight than a massive 3D complex acoustic fluid structure interaction, for example. Because the goal of simulation is not complexity, the goal is understanding. So the first step in simulation is not choosing the software, it is choosing the level of modeling. Can I reduce it analytically? Or do I need a numerical approximation? And if I approximate it numerically, do I need it to be 2D or 3D, and etc.? That decision alone separates engineering thinking from just button clicking. So let's move on to the numerical methods available. I'm gonna mention 5, but of course there are more, saving the most beautiful one to the last. Let's start with the most famous one, the finite element method. We've mentioned this method in the previous video, but briefly, the idea is this. We take our domain and we partition it in small elements, creating a mesh over the geometry. Then we choose an approximation of the governing equation in that local, and we use something we call a shape function. Then we assemble a solution of all the elements together to build a global system of equations that represent the whole physical problem. If you want an intuitive and visual explanation, there is an excellent video by the Efficient Engineer channel that explains it beautifully. And for deeper theoretical understanding, I recommend studying from the foundation references out there, like the work of P. Engard Boll in his book Introduction to the Finite Element Method, and the book of Finite Element Modeling for Stress Analysis by Robert D. Cook. There are of course more courses, but those are my favorite. Now let's move on to the finite volume method. In the finite volume, we take the integral form of the governing equation, use the divergence theorem to apply conservation on a local volume. Basically, for each control volume, we say what enters minus what leaves must equal what accumulates inside. So it studies the flux. This makes the method locally conservative by nature, and that is extremely important in fluid mechanics where conservation of mass, momentum, and energy is fundamental. That's why it's mostly used with computational fluid dynamics or CFD. Now let's move on to the finite difference method, which is probably the simplest numerical method conceptually. At its core, finite difference comes directly from Taylor series expansion. If you're an engineer, you must know this. The method basically states that if you have a derivative in your governing equation, you can replace that derivative with an algebraic approximation, that is, truncated form of Taylor expansion, using values at nearby grid points. For example, a spatial derivative can be approximated using the difference between neighboring nodes divided by the grid spacing. So instead of solving differential equation that might be difficult or impossible to solve, you end up with a simple analytical equation defined on a grid. Because of this structure, finite difference works well on simple structured domains like rectangular or regular geometries. However, it becomes difficult to apply when the geometry is complex. Let's talk about the other method, mesh-free methods. But let's first badmouth the finite element a little. One of the limitations of the finite element method appears when we deal with the very high gradients, for example near crack tips or in problems with large deformation. In these cases, the solution may require extremely fine mesh to capture the physics accurately. That means more element, more degrees of freedom, and heavier computational costs. And when the crack propagates, the mesh may need to be regenerated repeatedly. This is one of the motivations behind mesh-free methods. Mesh-free methods move beyond the idea of elements. Instead of dividing the domain into connected elements, the domain is represented by nodes distributed throughout the geometry. These nodes are not connected by predefined elements. Instead, each node interacts with the neighboring or surrounding nodes, often defined within a circular or radial region of influence. The approximation of the solution is constructed locally using these neighboring nodes. The shape of this influence domain and the mathematical function used inside it determines the specific mesh-free method. For example, some methods use polynomial basis function or exponential function or kernel-based approaches. Conceptually, the programming structure can look similar to finite element, but the foundation is different. While the FEM builds a mesh-free method builds a field of nodes. For deeper study, I recommend the book Mesh-Free Methods, Moving Beyond the Finite Element Method by G.R. Leo, one of the major contributors in this field. These methods are incredibly beautiful, and I will definitely do a separate video about it in the future. The fifth method is the Analytical Element Method, or AEM, and this one is particularly interesting. Unlike previous methods, AEM does not discretize the entire domain. There is no mesh filling or interior. Instead, the boundaries are only discretized and solution is constructed from analytical functions that already satisfy the governing equation. The method was first developed in the 1970s to solve groundwater flow problem, that is, the effect of the Tennessee Timbigee waterway, I hope I pronounced it right, on the surrounding aquifers. In AEM, the governing equation is Laplace's equation. Because analytical solutions to this equation are known, AEM builds the global solution by superimposing analytical elements, each representing a physical feature such as a boundary, a source, a sink, or heterogeneity. This is a cool software that uses the AEM called Anaxim. You can see how adding the elements changes the flow field in almost an instant. In this video, we took a small dive into 5 of the famous methods used for simulation. Of course, there are many more we're gonna see in the future videos. See you later, and thank you for watching.